Hi everyone, my name is Lin Zhang. Today I'm going to present our ICCV 2021 paper, MT-ORL, Multitask Occlusion Relationship Learning. This paper was carried out as Pan Hefeng's master thesis in Beijing University of Posts and Telecommunications, while Pan He was a student intern of Qi She in ByteDance, Beijing. Occlusion relationship reasoning is a highly challenging task for machines. It reveals relative depth orderings among the objects in the scene. It is composed of two subtasks, boundary detection and occlusion orientation prediction. Boundary detection aims to extract object boundaries from images. Orientation prediction aims to predict the direction towards a foreground object for each pixel. Finally, the predicted orientations are progressively accumulated only on the detected boundary pixels to recover the occlusion relationship in images. The first challenge of this task is how to utilize the limited coupling between these two subtasks in the decoder stage. On one hand, shared high-level features help these two branches to generate consistent outputs under the same semantic guidance. On the other hand, the two subtasks need to learn task-specific properties in the lower stage with larger spatial size. However, previous architectures, such as DOBNet and OFNet, overshare features in a larger spatial size between the two branches. We therefore propose an occlusion shared and path-separated network, as known as OPNet, which adopts a multi-scale structure and only shares information in deep stages of the decoder. The second challenge is a good representation for occlusion orientation. Some previous work represents orientation using continuous angles and use the distance function for loss computing. However, this results in angle periodicity problem, where angles with a distance of 2 times pi could produce large errors. Other work truncates the angles into minus pi to pi. Unfortunately, this also results in endpoint errors. That is, angles close to endpoint angles minus pi and pi produce large inaccurate errors. We therefore propose an orthogonal occlusion representation to predict the sign magnitudes of a horizontal vector and a vertical vector. As a result, our OPNet consists of 4 stages. At the shared encoding stage, an input image is first encoded by ResNet50. At the boundary detection stage, encoded feature maps are processed to produce side boundary maps at different scales. An orthogonal perception module with stripe convolutions and an occlusion shared module are introduced in this process. In the meantime, the orientation path also receives signals from OPN to produce an orientation feature map. The detected boundaries and orientations are then aggregated using non-maximum suppression to produce the final result. Our training loss is the sum of boundary detection loss and orientation prediction loss. The boundary detection loss is the weighted average of binary cross-entropy losses of a global boundary map and multiple side boundary maps at different scales. The orientation prediction loss is the smooth L1 loss of the sum of cosine and sine differences between predicted and ground truth orientations. We evaluate our method on the classic PIOD and BSDS datasets. Experiments show that our multitask method surpasses state-of-the-art OFNet consistently on both boundary detection and occlusion orientation prediction subtasks. Clearer object boundaries and more accurate orientations can also be seen on visualized images. To verify our architecture design principle, we did an ablation study on the number of shared layers and number of supervision scales. We found that sharing top 2 layers achieves the best boundary detection and orientation prediction results, validating our motivation to utilize the limited coupling between the two subtasks. The multi-scale supervision also plays an important role in experiments. We also plotted the curve between orientation recourse and angles on PSOD dataset. Our proposed orientation representation shows obvious improvement near the 2 endpoints, minus pi and pi. For more information, please check out our GitHub repository. Thank you.